Okay, so let's do a shear flow problem here. We've got this pipe. It's got a shear force of 8 kip. And we want to figure out what the shear flow in the pipe is at points A and B. So I'm just going to kind of redraw the cross section here. So if we were looking at point A, now we know the pipe, we know the neutral axis is going to be right there. We're looking at A. What is our shear flow at A? Well, okay, so our Q is equal to VQ over I. If we look at A, well then, what's our Q there? 0, because Q is equal to Y bar A, and the A there is 0. The area at that point is 0, because there is, if we go kind of all the way around, then once we get back up to A, the amount of area separated from the neutral axis is going to be 0. So QA is equal to 0. So fair enough. Now we need to figure out what it's going to be at B. So first off, let's figure out what our I is. So again, we are talking we're talking circles. So let's go to our chart here. So I is equal to 1 over 4 pi r to, no, I moved that underneath my face, did I? 1 over 4 pi r to the 4th. Now that would be for the entire circle. If we want to figure out what it is for the tube, and we just use I is equal to 1 over 4 pi RO to the 4th minus RI to the 4th. So, okay, we have, looks to me like the 6 inches here, that's the inside diameter. So, I is going to be equal to 1 over 4 pi times 6.0, sorry, 6 inches inside radius, not inside diameter, 6.02 inches to the 4th minus 6 inches to the 4th. So let's see, 6.02 to the power of 4 minus 6 to the power of 4. And 1 over 4 times pi times 17.4 inches to the 4th. So divided by 4 times 3.59, 13.64, and 13.6 inches to the 4th. That's our I. Now we need to know what our Q is there. So for the Q, we need to figure out what the centroid of this section here is. So I'm sure you'll recall kind of how, we know what the, we know we can look up the location of the y bar for a no. let me put that there. The location of the centroid for just a circle. So if we want to get to this semicircle thing, then what we need to do is just go ahead and use our go back to statics for last year. So let's y bar is equal to the sum of the essentially. So what we need to do is we need to treat this section in red there. We need to break it up into two. We need to break it up into a positive one, and we need to break it up into a negative one. And then just add the two y bar area, y bar times area contributions from each and divide by the total area. So our area for the outside, that'll be pi times 6.02 inches squared divided by 2, and then its y bar is going to be 4/3 times 6.02. Now, I'm writing under my face there again. Inches divided by pi. So this pi cancels out. This 2 cancels out. Yeah. So it's 2/3 times 6.02 inches cubed, plus the same thing for the negative section. So that'll be also 2/3 times its r to the third. All that divided by the total area. So that'll be pi over 2 times 6.02 inches squared minus 6 inches squared. Okay, so 6.02 to the power of 3 plus, minus, it should be a minus sign right there. Minus 6 to the power of 3 times 2/3. That's 1.44 inches to the third up top, all divided by 6.02 squared minus 6 squared times pi divided by 2 all over 0.378 inches squared, which squared cancels out to give us a third, give us inches. So 1.44 divided by 0.378, that gives us a y bar equal to 3.82 inches. Okay, so that is our y bar, this value here that we calculated right there, that's our a. So our q 3.82 inches times 0.378 inches squared. Oh yeah. I guess I should have realized that gives us what we had up there. Anyways, I guess I could have skipped a step if I realized that, but I'm not that bright sometimes. Anyways, 1.44 inch to the third is our Q. So we've got our Q, we've got our I, and we know our shear force. So our shear flow, okay, is equal to V times Q over I. I'll keep in mind that you know, we're not doing it over one cross section here. We're doing essentially that calculation was taking into account the you know, the Q going on above both these cross sections. So what we're going to need to do there is we're going to need to take that, divide that by 2 as well. So that's easy enough. 8,000 pounds was our shear load times 1.44 inches to the third. Times 2 times our I was 13.6 inches to the fourth. Q at B, therefore, is equal to 423.5 pounds per inch. So that's our shear flow. If we wanted to figure out kind of what the shear stress that'd be arising at that location would be, then what we need to do is we just need to take that and divide by that thickness. Wait. So divide by 0.02 inches. 21.2 KSI. And that'd be about